Assalamu alaikum. In this lecture, I will do two things. I'll give an example first to find the magnetic field for a circle located in the XY plane carrying current I. I want to find the magnetic field at any point in the space. To do that, first we note that this problem has phi symmetry, so therefore we will take first a special point in the xz plane where phi is 0. The first step in order to apply to we will find A, the magnetic vector potential A, which is given by this expression. The first step is to write the current density in terms of Dirac delta function, which is given by this. This is the field in the phi direction. Then we have to replace phi by minus sine phi dot I plus cosine phi dot j in Cartesian system, and then substitute here, and recognizing that because of the symmetry exists in the problem, we can show that the x component does not contribute, therefore we left with the j component in this case. Now we have a phi, which is given by this expression, which is in the direction of j. We will use for the numerator x minus x prime this expression, where cosine gamma is the angle between the field point and the source point, which is given by this. Note here, should be cosine phi minus phi prime, but we already take phi equal to 0, so we left with this expression. This is to the power 1/2. We substitute in this equation and carry the integration over r prime. We reach to this expression. Now now let's perform the integration over theta prime, and note that delta of cosine theta prime can be written in this form. Doing so, we get this expression. We still have to find this integration for the phi prime. Performing this integration gives us this results, where k of k and e of k are complete elliptic integrals given by this expression. K is now for a r sine theta over a square plus a r square plus 2a r sine theta. This is a summary of what we did in the previous lecture and the previous slides. Now to obtain B, we know that B is kernel A, so it has the radial component given by this expression and the theta component given by this expression. B phi is 0. We have also an A here, only one component, which is A sub phi. A sub r is 0, A sub theta is 0. For small k's, we can expand the elliptic functions, and this expression, the whole expression of phi is reduced to, this thing is reduced to pi k square over 16. To get this, you have to make an expansion and take k up to order of 4. So we have k in the numerator to the power 4, and in denominator to the power 2, we left with k square. This is a phi, and this is the approximation I did in the previous slide. This is, we have just find the make derivative to write b sub r and b sub theta. Near the axis of symmetry, we have theta much smaller than 1. Near the center also we have r much smaller than a. From the loop we have r much greater than a. Now far from the loop, the above equation reduces to this form. Pr is given by this and b theta is given by this. We define the magnetic dipole moment as I by a square over c. Here I just put a note that we can solve this problem using spherical harmonics. In this case, we have to express to substitute instead of 1 over x minus x prime by its expansion in terms of the spherical harmonics. Doing so and writing cosine phi prime as the real part of ei to phi prime, which means only m equal 1 will survive. So the integration over the primed quantity gives us just one of these m's. Doing so, and again note that for a fixed point in the xz plane phi is equal to 0, we have to put here in ylm theta phi is equal to 0, so we need ylm theta 0. After performing the angular part, we get here m equal 1. This is what we get. Now instead of PLM associated legend, I replace it by y1 of, because theta now is pi over 2, which is the xy plane, and phi is 0. So the final expression for phi is given by this term, where r smaller or greater is the smaller a or r radius of the circle or the loop, or the current loop, or r is the field point. Now this is here I'm giving the expression for y11 of pi over 2 and 0 is given by this. This is the final expression for a phi. Again, we can use this to find b sub r and b sub theta. We will get the same result as before. Now let's talk about magnetic fields of a localized current. This is a localized current distribution J of x prime, and this is the field point. We have to expand one, in this case, we have to expand 1 over x minus x prime to find the vector potential A. I'll use here Taylor expansion, which is given by this. So A can be written as contributed from 1 over r, from r prime over r cubed, and so on. This is a simplification of the above relation. Now I'll show that the first integral is 0, the second is the dipole term. The first thing, integral is 0 because we know that there is no magnetic monopole and it should be equal to 0. This is the contribution from the magnetic dipoles. Now for localized current J, we have divergence J equals 0. I am going to show that this is 0. Now we have a theory which says that for a divergence, vector V and fg2 scalar will behave function, this integration equals 0. To prove this, assume that divergence of AVG equals 0 because it's divergenceless quantity, and then distribute the divergence over the three functions. We get this, and in the final integral, note that we have divergence V as stated by theorem is equal 0. We will choose V to be G when we apply this to this expression, and I will choose F equal 1 and G xi prime. So doing so, we get this, and we get that the GID 3xi plus 0 equals 0, which means that the current the contribution from the first term is 0, which means that divergence B, which is consistent with divergence B, equals 0. The second term here, I'm writing it in terms of Cartesian notations. This is xj, x prime j, gid tau. Now in the above, I set x prime, fx prime j and gx prime I in the previous theorem. Doing so, we get this expression. Now simplifying, we finally reach to this expression. So which means that the second term, which this expression, can be written in this form. Epsilon ijk is the Zifta symbol, or it's a tensor of rank 3. Now finally we reach to this expression for the second term. Now let's define 1 over 2c of x cross j as the magnetization m. Then the magnetic moment is the integration of m over the 3x prime, which is given by this expression. Now substitute back and we get that A dipole is minus xm over r cubed, or mx cross x over x a cubed. So we write A, this is the first term, which is 0. This is the second term. Now for here I'm showing a circular loop in a plane xy. The magnetization for this is 1 over 3, implying the previous relation of cr prime across dl prime. dl prime is element length here, so we get ia over c. In the case of discrete moving charge, we have to write this in terms of Dirac delta function. So a dipole is m cross r over r cubed, which means that P now can be written as kernel of a dipole, which is given by this expression. That's it. Thank you.